Hmm. Okay, so I was checking if the link is working fine. Since it's already 3 minutes above the actual time, I think I can start the recording and then you can watch on YouTube since nobody has joined the live session. Okay, so maybe I'll wait for a couple of minutes. If nobody joins, then I'll just record the session and upload on YouTube. Hmm. Okay, let's start with the first problem. All right, so this is our first question. We are given an electron in hydrogen atom in its second excited state, and what we are asked to calculate is the magnetic moment produced by it due to revolution around the nucleus. And our options are these. Okay, so you can note that the magnetic moment is asked in SI units, which is ampere per meter square. So we do not need to worry too much about the units, and then we can begin solving our problem. Okay, so let's say this is our nucleus of hydrogen atom, which is just a proton, and let's say this is the ground state, and then this is the first excited state, and then this will be second excited state, right? So this will have n is equals to 1, this will have n is equals to 2, and this will have n is equals to 3. So this is the state which we will focus on, n is equals to 3 state. This is our second excited state. Okay, and we have one electron here. Okay, we have our electron here, and what we want to find is its magnetic moment. Okay, so first of all, what is magnetic moment? So magnetic moment, which is generally denoted as mu, okay, that is given by current multiplied by area. Okay, Now because this electron, this is revolving around the nucleus, so it will produce some current because it has some charge already, right? So we can write our current as charge upon time. So here, let's say the charge is E and time is the time period of revolution. Okay, and if v is the velocity, if it is moving with velocity v, then we can write current as E v over 2 pi r. Okay, where r is the radius. So this distance, this is r. Correct. So this is the current. What will be the area? Area is nothing but pi r squared. Okay. So both of them combined will give us mu as EV over 2 pi r multiplied by pi r squared. And this r will cancel out with one of the r's and pi will cancel out. So what we are left with is EVR by 2. Right? So let's write here mu is equals to EVR over 2. So this is our magnetic moment of electrons. Okay, now what we need to find is what is the velocity and what is the radius here. Now note one thing, from this Bohr's model we know that, okay, so from Bohr's model, let me box this one and let's write from Bohr's model, we know that angular momentum L, that is nh cut, or we can write mvr is nh cut or nh over 2 pi. Now note that we have this mvr, we have velocity multiplied by radius here and also here. Okay, so then we can write our mu as mu is equals to E, we will multiply with 1 m and we will divide by 1 m like this. And then for mvr we can simply plug in this value nh over 2 pi. So our mu becomes E nh over, now this 2 times 2 will become 4 pi m. Okay, now we know all the values, so just plug them in. E is 1.6 10 to the minus 19. N, we have already calculated that n is 3 here, so we will write 3. H is 6.626 10 to the minus 34, and then divide by 4 into 3.14, and mass of electron is 9.11 into 10 to the power minus 31. Okay, so if we solve this, we will get 3 into 6.626 into 1.6 divided by 4 into 3.14 into 9.11, and these powers will become 10 to the minus 22. Okay, and this factor in the bracket, this will come out to be uh, 0.28 into 10 to the power minus 22. So finally, we can write our mu to be 2.8 into 10 to the power minus 23 amps per meter squared. So this is our final answer. Okay, let's see if it matches with one of the options. Yes, so the answer will be C. Let's solve second problem, which is Bohr-Sommerfeld theory fails to explain which of the following. So our options are intensity variation of spectral lines, Zeeman effect, Stark effect, or all of the above. Okay, so what is intensity variation of spectral lines? So when better spectrometers were used, it was observed that the spectral lines which we are observing earlier, they are now splitted into even finer lines. So this was called fine splitting. Okay, and as discussed in the lectures, so this is discussed thoroughly, and this fine splitting could not be explained by Bohr-Sommerfeld theory. Therefore, it cannot explain A. What is Zeeman effect? Zeeman effect is splitting of spectral lines in presence of magnetic field. So when you apply a magnetic field to your system, let's say your hydrogen atom, then the spectral lines which we are observing, they split further, and this phenomena is known as Zeeman effect. Similarly, we observe a splitting in presence of electric field, and this is known as Stark effect. So both these phenomena are also not explained by Bohr-Sommerfeld theory. So the correct answer is all of the above. Okay, this was discussed thoroughly in the class. So if you have any doubts, please have a look at the lecture once again. Okay, so let's move on to the next one. Okay, so we are given a system and it is defined by the quantum number L is equals to 2. Okay, so L is equals to 2 corresponds to which orbital? L is equals to 2 corresponds to d orbital. So L is equals to 2 means d orbital. Okay, and now we are asked to write its z component, and our options are plus 2 h cut minus h cut, plus 2 h cut minus 2 h cut, plus 2 h cut 0 minus h cut minus 2 h cut, plus 2 h cut 0 minus 2 h cut. Okay, now what is Lz? Lz, so Lz is nothing but the z component of our orbital angular momentum L. Okay, and this is given by the magnetic quantum number. We have magnetic quantum number m. Okay, which gives us that Lz is nothing but m times h cut, and this m goes from minus L all the way up to plus L. Okay, so here because L is 2, this will imply m can have following values: minus 2, minus 1, 0, 1, 2. Therefore, Lz can have the following values: minus 2 h cut, minus h cut, 0, h cut, and 2 h cut. Okay, and all these angular momentum, all these orbitals corresponds to your 5 d orbitals. We know that there are 5 d orbitals, and all these corresponds to this. All these have different angular momentum Lz. So the correct option is C. Okay. Let's solve one more. So we are given a one electron system, which is a hydrogen-like atom, and then the electron in the hydrogen-like atom, it is in the d orbital. Therefore, it is referred to as d electron. Right? Now, what we are asked is what are the possible J values? Now, when the electron is in d orbital, okay, what does that mean? D orbital means our L is equals to 2. Okay, and what is the value of our spin? So spin for an electron, s, that is always 1 by 2. Okay, and the values of j for an LS coupling scheme, right, which is the your orbital angular momentum and your spin when they are coupled. So the values of j, they go from mod of L minus s all the way to L plus s. Okay, so what is 2 minus half? And then it will go to 2 plus half. That's all, right? So this will be 3 by 2 and this will be 5 by 2. So the correct answer is D. Okay, so we had our L is equals to 2 state like this. So this was our L is equals to 2 state, and then it has now split it in two states like this. So this is j equals 3 by 2 and this is j equals to 5 by 2. Okay, let's solve the next one. Fifth question. Okay, so we are given one state, and what is the state? The state is 2d 5 over 2. Okay, so what does this 2 mean? Okay, so this 2 means, so this is written as 2s plus 1 and this is equals to 2. This would imply that s is half. Okay, and this d would imply that, so spd 0 1 2, so L is equals to 2, and this 5 by 2 implies that our value of j, that is 5 by 2. Okay, this is similar to the last problem which we just solved. So here we had a d orbital, and because of spin orbit coupling we get these two states, j is 3 by 2 and j is 5 by 2. So in the current problem we are talking about this state, j equals to 5 by 2. Okay, you can see here that our j is 5 by 2 spin is half, L is 2. Okay, now what are we asked? We are asked to calculate the maximum possible value in degree. Maximum possible value in degree of orientation of j vector with z axis. Okay, so if j is 5 by 2, what are the possible values of mj? We know that mj, this is the corresponding magnetic number for j angular momentum. So it goes from minus j all the way up to plus j, right? So here we'll have m as minus 5 by 2, minus 3 by 2, minus half, half, 3 by 2, and 5 by 2. So we have all these 6 different values. Okay, and then how do we get the angle with the z axis? Okay, so if we draw our z axis like this, right? If this is our z axis, then what will happen? We have several. We will have 6 angular momentums corresponding to different values of mj, right? So we will have one here, one here, one here, one here, so on and so on, right? So these are our 6 possible orientations with respect to the z-axis, right? And then we are asked to calculate maximum possible value in degree of orientation of j vector. So we have drawn different j vectors corresponding to different value of mj, and we are asked what will be the maximum value theta. Okay, so you can already see that this will be our angle, so this will be the maximum angle, right? This will be the maximum angle. So this angle will be theta. Let's write this angle by theta. This will be the maximum angle. Okay, you can already see that this theta will be larger than 90 degree. So it's either option C or option D. Now how does the formula look like? So the angle cos theta for any value of mj, that is given by mj over under root j, j plus 1. Okay, and we are given j as 5 by 2. So let's solve this thing. Mj over 5 by 2 and j plus 1 will be 7 by 2. Right? Take a root here. So this will become 2mj over under root 35. Okay. So now when will this be maximum? So okay, I should also write the values here. So this corresponds to minus 5 by 2, minus 3 by 2, minus 1 by 2, 1 by 2, 3 by 2, and 5 by 2. Okay. These are the different mj values. And now you can see that this theta corresponds to the value of minus 5 by 2. So this is what we will plug in here. So our mj will be minus 5 by 2. Okay, so what this means is that our cos theta will be minus 5 over under root 35, or this implies theta is cos inverse minus 5 by 2, sorry, not 5 by 2, minus 5 over under root 35. Now if you solve this, you will get theta to be roughly 147.7 degrees, which is our correct answer. Hmm. Okay, let's solve next one, which is very similar to the problem that we just solved. So it states that the maximum angle of orientation, so we have to find out this maximum angle of orientation. Now this time we are asked for spin angular momentum, with external magnetic field. So we are given one external magnetic field, and the spin is given as S. For spin S is equals to, and then we are given options: 54.74 degrees, 125.26 degrees, 97.5 degree, and 145 degree. So these are our four options. Okay, let's solve this one. So we know that spin can have two values, either minus half. Okay, so here we are talking about the magnitude S, so that is always half for an electron, right? And then correspondingly the magnetic quantum number for spin, that can have two values going from minus s all the way up to plus s. So this will be nothing but minus half and plus half. So these are the two states. Now the external magnetic field, we are asked to calculate the angle with respect to external magnetic field. Let's say this is our external magnetic field, which is always taken along the z direction, and then because ms can have only two values, so the two vectors will look like this. Okay, this will correspond to minus half, and this will correspond to plus half. Okay, so as we have done in the previous problem, like here we had written this formula for cos theta, we can rewrite the same formula for the spin angular momentum instead of total angular momentum J. So what will be the formula here? So the formula here will be cos theta is equals to ms over under root s plus 1. Okay, so because we are asked maximum angle, that will be this value theta. So theta is this, and this corresponds to ms is equals to minus half. So our ms is minus half here. Okay, so now we can just plug in all the values. So this is minus half divided by under root s is half. So this is 1 by 2 into 3 by 2. Okay, so on solving this, we will get minus half into 2 divided by root 3, which is nothing but minus 1 by root 3. Okay, and then theta will be nothing but cos inverse of minus 1 over root 3, and cos inverse of minus root 3 over cos inverse of minus 1 over root 3 is equals to 125.26 degrees, which gives us our correct answer. So now let's solve the next problem, which is about Landau factor. So what are we given? We are given a single state. Hi Lakshman, thanks for joining. Otherwise, I was the only one today there in the class. Can you just confirm if my audio is coming to you, if I am audible, and if my screen is visible to you? Okay, thank you so much. Okay, so I have already solved 6 problems. Anyway, because this video will be uploaded on YouTube, you can watch there. And currently I am solving a 7th problem, but these problems are very unrelated, so it doesn't matter if you start from the 7th problem or not. But yeah, thanks for joining. So okay, the 7th problem which I am writing here is about Landau factor, and we want to calculate the value of Landau factor for a single state. So what is a single state? Single state is defined as, so single state is defined as s is equals to 0. This is the definition of a single state. Okay, now we know that our total angular momentum j, that goes from L minus s all the way up to L plus S. But when we put S is 0, so then J will be nothing but L, right? There is only one possible value for J, which is L, and it cannot have any other value. Now, if you remember about lambda G factor, lambda G factor is given by this formula: J plus 1, S plus 1, and minus L plus 1 divided by 2J plus 1. Correct? This is the formula. Now here we have already by definition have S is 0, right? So when we put S is 0, this term just becomes 0, right? And then we also have J is equals to L, right? We have J is equals to L. So these two terms, this one and this one, they become same, right? J plus 1 and this L plus 1, because J and L both are same. So both of them cancel out each other, right? So then our lambda G factor is nothing but 1 plus 0, right? So this is just all terms become 0. So this is 0, 0, 0. I should not write like that. So this is just 0, right? And therefore our G is simply 1. So the correct answer will be option B. Okay. Now before I move on to the next problem, uh, do you have any doubts or anything that you want to ask in the interaction session? Because this is meant to be interaction. If you have any doubts, you can ask and we can discuss that first. Otherwise, we can continue solving few more problems because we still have more than 1 hour left. Okay, thank you for your reply. Okay, so let's solve one more problem. So we are asked to calculate possible spectroscopic terms for energy levels of electron with L is equals to 2. Okay, and our options are okay. These are our options. So if you have watched the lectures, you will be familiar with this notation. So this subscript is nothing but, well, write subscript, which is written as here 3 by 2 or 5 by 2. That is nothing but the value of J, right? And superscript is value of 2s plus 1, and because s is half, right, s is half, so superscript will always be 2. Okay, and this middle symbol, which is written here either P or D, that is just L. Okay, so our notation is L to s plus 1 and j, like that. Okay, now we are already given L is equals to 2, right? We are given here that our L is 2. So what will that mean? So we have S, P, D, F, so on. This corresponds to L is equals to 0, 1, 2, 3, so on. So L is equals to 2 means we have a d orbital. Okay. So for the possible spectroscopic terms, our this notation should have d in the middle, right? So we can straight away eliminate option A, right? This is incorrect because it has P and P is L is equals to 1. Option B is okay. Option C has P, which is not allowed, and option D has P, which is also not allowed. So the correct option will be option B. Okay. Now we can also solve to get these two values of J. How? Because we know that J goes from mod of L minus S all the way up to L plus S. So here L is 2 and S is half. So this first term will become 3 by 2, and then we add 1, so this becomes 5 by 2, which is nothing but which is uh, nothing but L plus S. Okay, so these are the total values of J that we'll have, and you can see here that here we have 3 by 2 and 5 by 2. So if we write it in the standard notation, so because L is 2, we will have D here, and because spin is half, so this will be 2, and J can have 3 by 2 or J can have 5 by 2. So this is our answer. Okay. Feel free to stop me and ask if you have any doubts, or if you didn't understand the solution, I can explain it to you again. No problems. Okay. If not, we can move on to the next problem, which will be question 9 for today. Okay. So we have a Zeeman experiment, and can spin be any other number? Yes, it can be. So uh, spin actually depends on your particle. For example, if it is a fermion, okay, then it will have half integer spins. If it is a boson, then it will have integer spins, right? So I can give you one example. So electron always have half spin. It is the property of electron. So an electron cannot have any other spin except half. But if you take any other particle, like for example a photon, do you know what is the spin of photon? Okay, first of all, photon is photon a fermion or is it a boson? Do you know that? Boson, correct. So because it is a boson, so definitely it will not have a spin of half, right? That is not allowed. bosons have integer spins, right? So photon has spin 0. It is a special particle, right? Its spin is 0. Okay. So to answer your question, can spin have can spin be any other number? Yes, it can be any other number, but it will depend on the particle. So if it is an electron, its spin is fixed. It will always be half. If it is a photon, its spin is fixed. It will always be 0. So it will vary depending on the particle. But for a given particle, it remains the same. Okay. Could I answer your question? Uh, or uh, was your question about something else? Or maybe I misunderstood. Okay. Thank you. Mhm. If you have any other questions, you can type in the chat box, or also you can unmute your mic and ask, however you are comfortable. I'm fine with both. Meanwhile, I'll write the next question, and you can also think of any other doubts that you have. Okay, so this question is about Zeeman effect, right? So they are saying that in Zeeman experiment, Zeeman components are separated by 0.12 angstroms for a line of 5000 angstroms, and we are supposed to find the value of magnetic field in Tesla. Okay, and our options are 0.8, 1, 1.2, and 1.5. Okay, so what happens is in Zeeman experiment earlier, let's say we are getting one line. Let's say in the spectroscope we are observing one line, but then when you apply a magnetic field, this line splits. Okay, on applying a sorry on applying a magnetic field. So when you apply a magnetic field, this line splits in two parts, very fine two lines. Okay, and this the wavelength of this spectra that is coming out to be 5000 angstroms, and this tiny difference in the two wavelengths, let's say delta lambda, let's call this lambda, so that delta lambda is very small, it is 0.12 angstroms. Are spin and parity both the same? No. Spin and parity are not same. They are uh, different properties, as far as I know. Okay. So for parity, we generally talk in particle physics. I don't think it is. Uh, I don't think it is in syllabus. Yeah, but yeah, as far as I remember, both are different things. And when we talk about, so in particle physics, what happens is your particles can decay and they can form new particles. So there are some conservation laws, like how you have conservation of angular momentum, energy, all these things. So in particle physics, when we get new particles from heavier particles, then there are some additional laws which need to be followed. And there are several quantities which should be conserved, like bosonic number, fermionic number, so on. And parity is, if I remember correctly, it's been a long time. If I remember correctly, parity is also one quantity that needs to be conserved in a particle equation. So if you write an equation that earlier you had these particles and now finally you get these particles, so parity must be conserved. Okay. But yeah, I think parity and spin are not the same. They are different. Okay. Okay, so back to problem. So earlier we are observing spectra, and this is at around 5,000 angstroms. Now when we apply a magnetic field, this spectra splits into lines, and they are separated by a very small distance, which is 0.12 angstroms. So this is the delta lambda here. Now this delta lambda was discussed in the class. So this is your Zeeman splitting, and this delta lambda is given by this equation, EP lambda squared over 4 pi mc. Okay, so if we rearrange this, we will get B as 4 pi mc delta lambda over E times lambda squared. Okay, and now we just have to plug in all the values. So our B will be 4 pi, M is 9.11, 10 to the minus 31, C is 3 into 10 to the 8, delta lambda is given as 0.12 angstroms, so which we can write as 10 to the minus 10, and this whole thing divided by E is 1.6, 10 to the minus 19, and lambda squared will be 5000 into 10 to the power minus 10 whole squared. Okay, so let us now focus on this equation. So this will be just 4 pi into 9.11 into 3 into 0.12 divided by 1.6 into, so this 5000 squared, this will just become 25, right? And you can see that here you have 3 zeros, so this is 10 to the minus 7, and if you square it you will get 10 to the minus 14. Okay, okay, so let's write all the powers of 10 here, and above we will have, so here we have minus 31, and okay, here we also have minus 19 below, so minus 19 and minus 14 will become minus 33, right? And here we have minus 31 minus 10, which is minus 41, plus 8 is also minus 33. So these will just cancel out, and we are left with this. Okay, so we can just plug all these value in calculator, and what we will get is a value which is very close to 1. Okay, so we can write B as simply 1 Tesla. Okay, so the correct option is now. This is a very realistic problem. Okay, so this is if you do an experiment, for example, on sodium. So sodium D lines they are yellow in color, correct? So they appear at around I think 4900 angstroms, somewhere around that yellow. So this wavelength is very close to that. And then if you apply 1 Tesla magnetic field, okay, 1 Tesla magnetic field, which is actually quite large field. It is pretty strong magnetic field of 1 Tesla. And then what is the separation that we are getting? We are getting a separation 0.12 angstroms. So you can see that this is a very small number, 0.12 angstroms. This is 12 picometers, right? So this is such a small number. And to observe this splitting, therefore we need good spectrometers, right? Therefore, in the earlier times, when Balmer was observing hydrogen spectra, he could not, using his spectrometer, detect mm, this splitting, right? Because your resolution of your spectrometer that should be greater than, that should be smaller than 0.12 angstroms. If you can resolve wavelengths much below this number, only then you can get this value. So for Zeeman experiment, firstly, we need strong magnetic field. And then secondly, we need very high resolution spectrometers. Otherwise, we will not be able to observe this small shift. Okay. Any questions? Okay, thank you. So I'll then write down the next problem. Meanwhile, if you have anything to ask, please write in the chat box while I write down the next question. So the next question is regarding the fine structure. Okay, so the question asks that the fine structure of atomic spectral lines arises from, and we are given four options: electron spin orbit coupling, interaction between electron and nucleus, nuclear spin, or none of these. Okay, this was discussed in the class. Mm, can you write the answer in the chat box if you know the answer? There is nothing to solve here. If you know the answer, please write the option in the chat box. or you can even take a guess. That is fine. We are here to learn. This is not an exam. If we are wrong, then we learn better. Yeah, correct. Option A. Hmm. So this was, as I said, discussed in the class. Then that when we consider the spin orbit coupling. So earlier we have these quantum numbers S and L, but when they are coupled, we get total angular momentum J, which is S plus L, right? And because of this, when we take this into consideration, then we are able to explain the fine structure of atom. Now, bonus question is, when we consider the interaction between electrons and nucleus, what what do we get then? Okay, so this is not yet discussed in the class. Okay, but when you have a fine structure of atom, okay, so firstly we have just, let's say, one state like this. We have one spectral lines. So we have seen that this gets splitted, right? This gets splitted like this. So we call this fine structure. Now this thing gets splitted further up. Okay, this can get splitted further up. And do you know? And this happens because of interaction between electrons and nucleus. When we consider nuclear spin, that nucleus also has its magnetic properties, and we also need to consider the effect of nucleus. Okay, so then we get this further splitting. Okay, do you know what this further splitting is called? So this one was fine structure, and now each fine structure is splitted further. Okay, and it has a name which is very similar to fine structure. It sounds like fine structure, and it was mentioned in the class, but it is not yet discussed. Maybe it will be discussed in the upcoming classes. Okay, so this further splitting of fine structure, this is known as hyperfine structure. Hmm. Okay, so this is hyperfine. So earlier we had just one spectral line. Then we considered, okay, let's consider spin orbit coupling. Then from consideration of electron spin orbit coupling, we are able to explain the fine structure. Then we observe in our experiments even further splitting of fine structure, which is known as hyperfine structure. And to explain this thing, we need to consider the interaction between electron and the nuclear spin. Okay? So this option B and C, they contribute to hyperfine structure. Okay. So this was just some additional information. And I think this will be discussed later in the upcoming lectures. And then we can solve some problems afterwards. Okay. So I'll write down the next problem. Meanwhile, if you have anything to ask, please type in the chat box. Okay. So we are given that we have one electron atom, which is a hydrogen-like atom, and we are given n is 3. So this is our principal quantum number, n is 3. So let's write that down here. So if our n is 3, what will be our possible values of L? L can be 0, or L can be 1, or L can be 2. Okay? When L is 0, okay, okay, you already got the answer. Very good. Okay, I'll just solve it anyway for our YouTube viewers. So this L012, let's write down the corresponding values of ML. So when L is 0, our ML is 0. When L is 1, we will have -1, 0, and 1. And for L is 2, we will have -2, -1, 0, 1, 2. Because ML goes from -L all the way to +L. Right? So L is equals to 0. This is written as S, 1 is written as P, and 2 is written as D. And what is our standard notation? Standard notation is 2s plus 1 J, right? And what is 2s plus 1? Because S is half for electrons, as we just discussed. So we can simply write this as 2Lj. So L can have different values, S, P, or D. L can be written in terms of S, P, or D. And now we only need to find the values of J. Okay, and J is nothing but, okay, so J is nothing but L plus S. Okay, so it goes from mod of L minus S all the way up to L plus S. Okay, so here L is 0. L is 0. So it can only have one value, which is L plus S. So here our J will be just half. Here L is 1. So it can have two values, 1 by 2 and 3 by 2. And here L is 2. So it can have three values, 3 by 2 and 5 by 2. So these all corresponds to L plus S and L minus S. Okay. Now everything is solved, so we can just write down all these 5 terms here. So first one we can write as 2s half. This will be 2p half and 2p 3 by 2. This will be 2d 3 by 2 and 2d 5 by 2. Okay. So the correct answer is option A. Okay. Let's solve next one. This will be 12, I guess. The spin orbit splitting is proportional to z to the power n. Okay. What is n? And your options are -1, +1, 2, or 4. So here z is your atomic number. Z is the atomic number. So Z is 1 for hydrogen, and then as we go down in the periodic table, Z keeps increasing. Correct? So what we are asked is, how is this spin orbit splitting? How does it depend on Z? Do you know the answer to this one? No. Okay. So then let's solve it. So first of all, let's consider one electron and one nucleus. Yeah? Let's say this is our nucleus, the bigger one. And here we have one electron. Let me draw it by blue. Okay. So this is the electron and this is revolving around the nucleus. Right? So here what we generally consider, we consider that our nucleus, this is at rest, right? So let's say this is the nuclear frame of reference. Nuclear frame. Now what we can do is we can also observe from the electron, right? Because it is just a frame of reference. We can change our frame of reference from nuclear frame to electron frame. Okay, electron frame. Now what will happen in the electron frame? The electron will be appearing to sit in the center. So electron will appear to be at rest, right? And we will have the same orbit. But now the nucleus will appear to be rotating around the electron, right? Like this. So is this fine? So now electron is at rest. Our electron is at rest, but nucleus is orbiting the electron. Okay. So now this orbiting nucleus, this constitutes a current which gives rise to a magnetic field at the origin. Okay. So because this neutron is revolving around the electron, it is moving with some velocity, let's say v. It is moving with some velocity v. So it will constitute some magnetic field. Now this magnetic field B, this magnetic field B is given by this E cross V divided by C square, where your E is minus grad of V, which is nothing but minus r cap dvr by dr. Okay, so this is the, so E, this is the electric field. Electric field at the electron due to the nucleus, and Vr is the corresponding potential energy. Okay, so this equation comes from relativistic interaction between electric and magnetic field, which we will not go in much detail. Okay. Now what happens is that this magnetic field interacts with the spin of electron, and then we get one Hamiltonian like this. So let's write SO for spin orbit. So this Hamiltonian will be half mu dot B. Okay? And then we can plug in the value of B and mu. So this will be E h cut squared over 2 MEC squared R dV R by dr and S dot L. Okay? Where the angular momentum is given by h cut L and the magnetic moment mu. So here our mu we have taken GE h cut over 2m times S. Okay, and our h cut L, this was taken to be ME R cross V. Right? So then we get the following Hamiltonian. Also note that 1 over R dVr by dr, this is nothing but the potential, which is given as d over 4 pi epsilon naught, and instead of r square we will have now r cube. Okay, and for electronic states with quantum numbers, so the expectation value of 1 over r cube, that goes as z cube over a naught cube n cube l plus 1 and l plus half. Okay, so here note that this value 1 over r dvr, okay, this is this is proportional to z over r cube, and here we have found out that this 1 over r cube, this 1 over r cube goes as z to the 3, right? So finally we can write that our spin orbit coupling, this is proportional to z over z into, let's say, r cube, and this will be then proportional to z to the power 4. So the correct answer will be option 4. Okay, so this is so this is what people generally remember, that it goes as z to the power 4. Otherwise, to get the correct answer we have to go into relativity and then calculate this Hamiltonian, and then after we have calculated the Hamiltonian we need to calculate the expectation value of 1 over r cube, and then we get this proportionality as z to the power 4. Okay, but now since we know this thing, so then we can solve some problems related to this. So for example, we can solve one problem that if fine structure splitting between 2p3 by 2 and 2p1 by 2 levels in hydrogen atom is 0.4 per centimeter, the corresponding splitting in Li2 plus will approximately be, and here we have four options: 1.2 per centimeter, 10.8 per centimeter, 32.4 per centimeter, and 36.8 per centimeter. Okay, so for hydrogen, Z is 1, and for lithium, Z is 3. And we already calculated above that this delta E, this is proportional to Z to the fourth. So this delta E is proportional to Z to the power 4. So therefore we can write delta E of lithium over delta E of hydrogen. This will be Z of lithium over Z of hydrogen to the power 4, which is nothing but 3 over 1 to the power 4, or 3 to the power 4, which is 81. Now we are given delta EH as 0.4 per centimeter. So our delta E of lithium will be 0.4 into 81 per centimeter. Now if you multiply, you will get 32.4 per centimeter. So the correct answer is option C. Okay, let's solve next problem. So we have two lines in sodium, right? We have D1 and D2 lines of sodium. This was discussed in the class. And we are asked to calculate the ratio of intensities of these two lines. So what is the ratio of intensities of the D1 and D2 lines of sodium at high temperatures? Okay, and our options are that both are equally bright, 1 is to 1, or 2 is to 3, or 1 is to 3, or 1 is to 2. Now, how do you get the sodium D lines? So what is the transition? So for the D1 line, the transition happens, if you remember from class, transition happens from P1 by 2 to S1 by 2. Okay, let's write 2 here. And for D2 line, the transition happens from 2P3 by 2 to 2S1 by 2, right? So we have these P levels, and these P levels get splitted because of this spin orbit coupling, and we get two different p levels. So this is 2p 1 by 2 and this is 2p 3 by 2, and this 2p 1 by 2. Okay, and the below one is just 2s 1 by 2. So this transition from 2p 1 by 2 gives us d1 line, and this transition from 2p 3 by 2, this gives us d2 line. Okay, now to calculate the intensity, we should know that this is a p orbital, right? This is a p orbital and this is uh, s orbital. Okay, so when this splitting happens, how many number of electrons goes into different states, right? So for example, this s has two electrons and both of them can go here. Okay, so this can have two states and they remain as it is. But p, if you remember, it has three orbitals, px, py, pz. So in total, there are six states, right? And after splitting, what happens is four will go here and two will go here. Okay, and how do you get it? So mathematically speaking, one can write intensity of d2 over intensity of d1. This will be equals to 2 times j2 plus 1 and 2 times j1 plus 1. So if you know j, so the intensity I is proportional to 2j plus 1, because this is how many electrons can be occupied in that particular energy level. Okay, so then here we have j2 is 3 by 2 and j1 is 1 by 2. So this becomes 3 plus 1 and this becomes 1 plus 1. So this is 4 over 2, which is nothing but 2. Okay, so the correct answer will be option D, that the D1 to D2 ratio will be 1 is to 2. So the D2 line which we will observe will be 2 times brighter than the D1 line. Okay. Let me write down the next one. So we are asked about the splitting between 2p 3 by 2 and 2p 1 by 2. Okay, so our options are 3 by 2 alpha h cut squared, half alpha h cut squared, 3 by 2 alpha h cut to the power 4, or 5 by 2 alpha h cut squared. Okay, so we are given that the spin orbit interaction h, that is alpha times L dot s. Also, we know that our total angular momentum j, that is also L plus s. Therefore, we can write j squared as L plus s squared, and this will give us L squared plus s squared plus 2 L dot s. Right? So from here, we can write L dot s as half j squared minus L squared minus s squared. Therefore, our interaction becomes alpha times 1 by 2 j squared minus L squared minus s squared. Okay, so now once we have this value of interaction, so we can easily calculate the splitting between 2p3 by 2 and 2p1 by 2. We just need to plug in the values of j, L and s. Okay, so let's start with 2p3 by 2. Okay, 2p3 by 2. Okay, here s is half, right? So this will give s squared as s plus 1 h cut squared. So let's put half here into 3 by 2 into h cut squared. So our s square is then 3 by 4 h cut squared. Okay, because it is p, so L is 1, L is 1, so then our L square will become L plus 1 h cut squared, right? And if we put 1 here, so this will be 1 2 2 into h cut squared. So our L squared is simply 2 times h cut squared. So for 2p3 by 2, our value of j will be 3 by 2, which implies that j squared, which is jj plus 1 times h cut squared, this will be 3 by 2 into 5 by 2 into h cut squared. Okay, or j squared will be 15 by 4 h cut squared. Therefore, if we calculate the value of h for 2p3 by 2, this will be nothing but alpha over 2, 15 by 4 minus 2 minus 3 by 4 h cut squared. Okay, so 15 by 4 minus 3 by 4 will give us 12 by 4, and 12 by 4 is 3, 3 minus 2 is 1. So this simply becomes alpha h cut squared over 2. Now we can repeat this same exact procedure for 2p 1 by 2, whatever we have done. So for 2p 1 by 2, s is half, so s squared will come out to be same, which is 3 by 4 h cut squared, right? Then L is 1, so our L squared will again come out to be same, which was 2 h cut squared, but now J is half instead of 3 by 2. So our J squared will change. So our J squared will now become 1 by 2 into 3 by 2 into h cut squared, which is nothing but 3 by 4 h cut squared. Correct? Therefore, h 2p 1 by 2, this will become alpha over 2, 3 by 4 minus 2 minus 3 by 4 h cut squared. So this will cancel out and this 2 will also cancel out. So this will be nothing but minus alpha h cut squared. Okay. And now we want to, what do we want to calculate? We want to calculate the splitting between these two levels. So we want the difference of energies, delta H, right? So our delta H, this will be H of 2p 3 by 2 minus H of 2p 1 by 2, and this value is alpha h cut squared by 2 minus alpha h cut squared. Okay, so this will simply become, if we take out this common, this will become half plus 1, or this will be simply 3 by 2 alpha h cut squared. Correct? So the correct answer will be A, 3 by 2 alpha h cut squared. So because we have now calculated these energies, what we can actually do is we can see how this splitting is happening. So let us say this was our L is equals to 1 or p orbital. Now when we consider spin orbit coupling, let's say this is the same energy, we get two states, right? We get two states. One is half alpha h cut squared. So this is, let's say, half alpha h cut squared, and the other is minus alpha h cut. So somewhere here, this is minus alpha h cut squared. So our states now, they look like this. Okay. So this distance, this energy separation, this is half alpha h cut squared, and this energy separation is minus alpha h cut squared. Okay, and if you calculate the degeneracy, which is nothing but 2j plus 1, 2j plus 1, here j is 3 by 2, so this will come out to be 4. So here it will be 4. So this can so 4 electrons can occupy these energy levels, and here you will get 2. So 2 electrons can occupy these energy levels. So what is happening is your p orbital has now split it up in two different orbitals, which is known as p1 by 2 and p3 by 2. Now 4 of the electrons out of total 6 electrons, here we had 6 electrons in the p orbital, right? Now 4 of the electrons have gone to higher energies and 2 of the electrons have gone to lower energies, right? So these final states, they are called as 3 by 2 and 1 by 2. Okay. Similarly, if it were a d orbital, then that could have contained 10 electrons here, and again that will split like this. Now, of course, this splitting will be different, right? These energies, they will be different what they are from p orbital. One can calculate using the similar logic which we have used to calculate the p orbitals, right? But the point is, this will become d3 by 2, this will become d5 by 2, and this state will have 6 electrons, and this one will have 4 electrons. And then in similar way, you can do for f orbitals, g orbitals, and so on. Okay, so these energies we can just calculate using same logic. So instead of L as 1, we will have L as 2, and instead of J as half, we will have J as 3 by 2 and 5 by 2. Okay, everything else remains the same. So this one can try on their own and find out the values. What is the ratio of this splitting, and what is the value of this splitting in terms of sin orbit strength alpha. Okay, so this was the last question for today. If you have any questions, you can ask, you can type in the chat box. Also, for people watching on YouTube, if you have any questions, you can ask in the forums or in the YouTube comments, or I am writing my email ID here once again. So it is just my name, Manav Peniwal at isc.ac.in. Okay. So yeah, that is it for today's lecture.